So welcome to the new lecture of Basic Electrical Engineering. So in this lecture, we will discuss about the equivalent circuit of the practical transformer with reference to the referred values. So this lecture will cover the concept of equivalent referred parameters of the transformer. We will see that how we can get one equivalent circuit of a practical transformer in terms of the primary and secondary parameters collectively. So as you can see here that the equivalent circuit of a practical transformer is shown in this diagram where all the relevant parameters have been given, like I1 is the primary current, V1 is the primary voltage, and so on. However, you can see that there is one current which is I2 dash, which is equal to I2 by A. Now, what is this basically? So in our previous lecture, we have already studied this concept that when the transformer is loaded basically, so what happens when you load the secondary winding of the transformer by connecting it to some load, right? And the primary winding is connected to the supply. Primary current is flowing here, secondary current is flowing in this particular winding. E2 is the EMF induced in the secondary winding because of mutual induction, and E1 is the EMF induced in the primary winding because of self-induction. Now what happens when this current starts flowing in this particular winding? It starts generating its own flux, which opposes the main flux. So main flux is coming from this side. So this flux, which is, let us say, phi 2, opposes the main flux phi naught or phi, whatever notation you can take. Now what happens when this phenomena happens? This tries to weaken or reduce the strength of the main flux, which in turn reduces the strength of this EMF induced in the primary winding. Now to maintain, now because the power on the primary side and power on the secondary side shall be same. This is an assumption basically which is taken for a transformer, as it is been discussed in previous lectures also, that a transformer transfers the voltage from one level to another level at same frequency, same power, right? So to have the same power, we need to keep the strength of this voltage induced EMF maintained in the primary winding. Now to do so, what happens? The primary voltage basically, because now what in this situation, what will happen when E1 reduces, so V1 becomes greater than E1, to send more current to the primary winding, an additional current basically. And this additional current is, let us say, I2 dash. Now what it does, it nullifies the demagnetizing effect of I2. Why? Because I2, it produces its own flux in secondary winding, which is, let us say, phi 2. Phi 2 opposes main flux phi. Phi reduces, and as a resultant, E1 also reduces. So we get this thing. So V1 become equal, V1 become greater than E1. So now what I want you to understand here is that the secondary current basically has, now this I2 is affecting the primary winding operation, right? So that means all these parameters have their effect on the either side. Okay, so we can say that all the secondary winding parameters have or influence the primary winding parameters or working, and vice versa, right? Vice versa means primary winding parameters also influence the secondary winding working, right? Now this is what we leads to the fact that these two windings or can be replaced by a single circuit. So it is possible to obtain a single circuit because here we have two circuits. This is one, this is one. So this is primary circuit and this is the secondary circuit. So we can combine these two and we can get a single circuit by using the equivalent referred values. Now let us understand what is this basically. Now how do we get this I2 dash is equal to I2 by A? This is also a question. Okay, so how we got I2 dash is equal to I2 by A? So this is a question mark. So this is what we will understand in today's class, right? So for example, this R2 has a resistance which is, let us say, R2 dash. This R2 dash is basically the referred or reflected value of R2 in primary, right? So it means that this R2 has some influence in the primary winding, and that influence is basically because of R2 dash in the primary winding, right? So this means that R2 dash does the same thing in primary winding as R2 does in secondary winding. Means whatever effect R2 has in the secondary winding, the same effect is uh, seen in the primary winding because of R2 dash. So what is the effect of R2 in the secondary winding? So the effect of R2 in the secondary winding is I2 square R2. So this is the heat effect basically. What is R2? R2 is the resistance of secondary winding. R1 is the resistance of primary winding. R2 dash is the value of R2 reflecting in primary winding. So R2 is responsible for the heat effect in the secondary winding, right? So that means I2 square is into R2 is equal to I2 dash square into R2 dash. So that means these two effects are same. So from here we can find out the value of R2 dash. So R2 dash is equal to I2 square by I2 dash square into R2. So this could be written as I2 divided by I2 dash square into R2, right? So this is, let us equation number one. So that means the effect of R2 in primary winding can be seen as R2 dash, which is equal to the square of the ratio of the two currents, the secondary current and the primary counter current. So this current basically counters the effect of I2, right? So now, as we know that the power on the two side of the transformer is same, so let us take it E1 I2 dash. So the power on the two side of the transformer is same. Now you can you would be in confusion that why we are taking I2 dash. So why I2 dash instead of I1? So this could be the question in your mind. So the answer is I2 dash is one component of I1. Other component is of I1 is I naught, right? Now I2 dash is assumed to be flowing in the winding, keeping the strength of E1 equal, countering the effect of I2, right? So it is performing all those functions, necessary functions in the primary winding, which are required to be done by I1. So it is nothing but I1. Now, as you can see that I naught is very, very less than I2 dash. So if I1 is equal to I naught plus I2 dash, so I1 is almost equal to I2 dash. So it is one and same thing basically, because more than 95% of the current is I2 dash, right? If you apply KCL at this particular point. Now, the power on both sides of the transformer is same. So from here we can say that I2 by I2 dash is equal to E1 by E2, right? So if it is E1 by E2, so E1 by E2 is equal to um, it is equal to K or A. In some books you will find it as K, in some books you will find it as A, right? So this is transformation ratio, right? So we can replace this in equation 1. So the equation 1 can be written as R2 dash is equal to A square R2. So this is the one point. So let us say this is equation number 2, right? Similarly, so we'll write it once again here. So R2 dash is A square R2. So this is our some equation, right? Equation number 2. Now similarly, we have this X2 in the secondary winding. So X2 also has its referred value in primary winding. That value is, for example, X2 dash, right? So it means that the effect which X2 has in the secondary winding, the same effect uh, X2 dash will have in the primary winding of the transformer, right? So the effect of X2 in the secondary winding is, it is I2 square X2. So it is equal to, these two effects are same. So I2 dash square into X2 dash. So from here you can find out X2 dash, which is equal to I2 square by I2 dash square into X2. So we can write it as I2 divided by I2 dash whole square X2. So it is equal to A square X2. So we'll write it here also the same thing, right? So X2 dash is equal to A square X2, right? Now, so that means if we say that instead of drawing these two circuits separately, we want to merge these two circuitries into a single circuit. So we need to add these two resistances R2 dash and X2 dash reactance in the primary winding, right? Now we will understand that concept also. Now, as we know that the power on the both sides of the transformer E2 into I2 is equal to E1 into I2 dash, both the power is same, right? On both sides of the transformer, right? So we can rearrange this. So E1 is, let us say, equal to I2 by I2 dash into E2. So this is equal to E1 is equal to AE2, right? So this is another equation, right? So this is one equation, this is second equation, this is some another equation, right? So as we know that the ampere turns on both sides of the transformer are same, hence I2 T2 is equal to I2 dash T1, or I2 dash is equal to I2 T2 by T1. So I2 by A, because T2 by T1 is 1 by A, right? Now, how did we get this one? Because we know from the transformation ratio, voltage to turn ratio, E1 by T1 is equal to E2 by T2. So E1 by E2 is equal to T1 by T2 is equal to A or K, right? So notation could be any. So now from here we have few equations, and these equations are like uh, R2 dash is equal to A square R2, X2 dash is equal to A square X2, E1 is equal to A E2, right? And I2 dash is equal to I2 by A. So these are basically the equivalent referred parameters of primary winding. This means that all the resistive or impedance parameter of the secondary winding will reflect to primary as the product of square of the transformation ratio A and the respective impedance parameter, right? So you can see here R2 dash is equal to A square R2, X2 dash is A square X2. Similarly, you can say that the EMFs will reflect as the product of transformation ratio and the respective EMF, like here, and currents will reflect as the ratio of the current to the transformation ratio, right? So this is how we will take the parameters of the secondary to the primary winding. And now let us see how the circuit will look like. So this is how the circuit will look like. Now what we have done, basically we have removed this particular part. So by removing it, we have merged the two circuits, right? As you can see, we have replaced R2 with a square R2. We have replaced X2 with a square X2. We have replaced I2 dash with I2 by A basically. And the voltage V2 will reflect in primary as product of transformation ratio and the voltage. The voltage E1 is A E2, right? And all these parameters are same, right? So now if you see in this particular diagram, everything is same, but only the difference is that we have merged the two circuitries. Now this is a single equivalent circuit of practical transformer on load, right? Now this is the impedance basically, right? And this is also the impedance. This is Z1, for example. This is, let us say, Z2, or we can say A square Z2, right? Because if Z2 is the impedance of the secondary winding, so it will reflect in the primary winding as Z2 dash, which is equal to A square Z2. Because all the resistive components, you can see the order is that these are being multiplied by square of the transformation ratio, right? Similarly, the current, basically this, uh, right? So now vice versa will happen when we have the uh, secondary equivalent circuit with respect to primary, right? So we will see that also. Now if we see here, this current I1 is equal to, now if we apply KCL at node X, so it is equal to I1 is equal to I naught plus I2 by A, or I2 dash, right? Now as we know that I naught is only 2 to 5% of rated I1. Hence, I naught is very, very less than I2 dash. So, I1 is almost equal to I2 dash. So now what we can do is we can shift this part towards this side so that we can combine these parameters with these parameters, right? So we can shift the core parameters or core parameters circuits, that is R naught and X naught, between junction X and Y to the input side, right? So we will shift this one and we will see this is how it will look like. So what we have done earlier, this circuit was at this particular point, so we have shifted it towards this side because of the fact that I1 is almost equal to I2 dash, right? Now when I1 is almost equal to I2 dash, we have shifted it toward this side, so now we have these parameters in series. Okay, so these all parameters are series, right? Now what we can do, we can add R1 plus A square R2. So this will give me R effective 1. So RE1 is the effective resistance of the primary winding. Similarly, RE, sorry, XE1 is X1 plus A square X2, and ZE1 effective impedance, it is equal to Z1 plus A square Z2, right? So XE1 is the effective reactance, right? So now when we do so, we will get this circuit with us. So this is RE1, where RE1, as I mentioned earlier, it is R1 plus A square R2, and XE1 is X1 plus A square X2, and ZE1 is Z1 plus A square Z2. So this is the approximated equivalent circuit of a transformer referred to primary. Now what you can see here, that earlier we had two circuits. Okay, so we had two circuits here. Now we have two circuits of the transformer, but now we have one circuit. Now how it became possible? Because what we have done, we have merged the two circuits into one by considering the equivalent referred values of the secondary winding into the primary winding. Now we will see that how the second, if we now earlier in this case, what we have done, we have merged the secondary winding circuit into the primary winding side, right? Now what happens, or how will we merge the primary winding circuit to the secondary winding side of the transformer? Now this is the question. Now this we will see in this particular slide. We will see how we will merge the primary side into the secondary side, right? So now because in the beginning we have seen that the parameters of the primary winding also influence the working of the secondary winding of the transformer, right? So now let us say that R1 dash is the value of R1 reflecting in the secondary winding, right? That means this R1 dash is the referred value of R1, right? So that means R1 dash will produce same effect or effects in the secondary winding as R1 produces in the primary winding, right? So now let us see what happens when we consider this case. So the effect produced by primary winding in the effects produced by R1 in primary winding is I2 dash square into R1 is equal to uh, I2 into R1 dash, right? So now R1 dash is equal to I2, sorry, this square, I2 dash square divided by I2 square into R1, or R1 dash is equal to I2 dash divided by I2 into R1. As we already know that, so this is square. So as I2 by I2 dash is equal to A, so I2 dash by I2 is 1 by A, right? So R1 dash is equal to 1 by A square R1, or R1 dash is equal to R1 by A square, right? Now, similarly, this this X1 will produce some effect in the secondary winding, right? So this effect X1 has a referred value, that is X1 dash in the secondary winding. So we can say that I2 dash square into X1 is equal to I2 square into X1 dash, right? So these two effects will be same. Okay. So from here we can find out X1 dash, which is equal to A square X1. So this is one thing. Similarly, this Z basically, uh, the impedance will also have the same effect. Now, okay, now we know that E1 into I uh, 2 dash is equal to E2 into I2. So from here you can find out E2 now. So E2 is equal to E1 I2 dash by I2. So E2 is equal to E1 by A. Okay. So this is one thing. Now we also know that I2 dash into T1 is equal to I2 into T2. So from here you can find out I2. So I2 is equal to I2 dash into T1 divided by T2. So T1 by divided by T2 is A. So it is equal to, so I2 dash I2 is equal to I2 dash into A, right? And I naught dash is equal to I naught into A. I w dash is equal to I w into A. I mu dash is equal to I mu into A, right? And I1 dash is equal to I1 into A. So that means all the, now you can see the trend here. The trend says that the resistance of primary winding when reflecting in secondary, it will always be divided by a square of the transformation ratio. The reactance of, uh, this is wrong, sorry, it is x1 by A square, right? So this is wrong here. So the reactance of the primary winding when reflecting in the secondary winding will always be divided by square of the transformation ratio. When EMF of the secondary winding, induced EMF of secondary winding will always be ratio of the primary induced EMF divided by the transformation ratio. The current in the primary winding when reflecting in secondary will be multiplied by the primary current. All the currents will be multiplied by the transformation ratio. Okay. Now this is how it will happen. Now by considering all these things, uh, the approximated equivalent circuit referred to the secondary of a transformer is drawn like this. So first of all, we will draw the equivalent circuit of the practical transformer considering the parameters as it is, right? So this is the core, this is the primary winding here, and flux, secondary winding, and the parameters of secondary winding, right? And then load impedance is connected on this side. So this is load ZL. Okay. So this is R2, this is X2, I2, E2, V2, this is I2 dash, and here we have primary EMF induced E1, this is R node, this is X node, this is no load current, this is the uh, full component, reactive component of no load current, this is magnetizing component of no load current, this is R1, this is X1, and here we have V1, and this is the primary current I1. So this is the complete equivalent circuit of the transformer on the load condition. So these are the two junctions X and Y, for example. Now when we merge this into this, right? So what will happen? It will look like this one. So first of all, we have the core parameters, right? And then we have this. This is R1 dash. This is X1 dash. And then we have this is R2. This is X2. And then we have the load impedance here, ZL, right? And this is the current I1, which is, or I1 dash, for example. And here we have the current, which is I2, and here we have the current I naught dash, here we have the current IW dash, this is I mu dash, and it is X naught dash, and it is R naught dash, and this is equal to, now this is E2. Now we will, when we will merge this, so this E2, because this is the input of the secondary winding here, because we are merging the primary side into the secondary side. So this E2 will be equal to V1 by A. Okay. So now this is how it will look like. Now what we can do is we can add these resistances together. We can add these reactances together. This is Z1 dash. This is Z2, right? So by adding all these and replacing these parameters, like I1 dash will be equal to I1 into A, I naught dash is equal to I naught into A, and similarly I mu will be equal to A I mu, because all the currents, when we are merging the primary side into the secondary side, all the currents of primary will be taken as the product of transformation ratio and primary current into secondary, right? So I to W dash will be IA IW, and this R naught will be, now we are dividing this by square of transformation ratio. X naught will be X naught by A square. R1 will be equal to R1 by A square. X1 dash will be equal to X1 by A square. Z1 dash will be equal to Z1 by A square, right? So now we will, and here we have the terminal voltage V2, right? Now we will see when we combine all these, so the circuit will look like this one. So these are the core parameters, right? And then we have the resistance, which is RE2. Then we have the reactance, which is XE2. And then we have the load impedance, ZL. So this is load. And here we have V2, right? And here we have I2. Now here we have a I naught, this is a I mu, this is x naught by a square, this is r naught by a square, this is a I w, and this is the input side, so it is equal to v1 by a, right? And this is the junction x, this is junction y, and the current here is ai1, and this is ze2, right? So uh, we have combined all these parameters. Now we have added all these parameters together. So here re2 is basically equal to r1 dash plus r2, so it is equal to r1 by a square plus r2, right? Similarly, xe2 is equal to x1 dash plus x2, so it is equal to x1 by a square plus x2. Similarly, ze2 is equal to z1 dash plus z2, so it is equal to z1 by a square plus z2, right? So this is how we can combine or merge the two circuits of the transformer into a single circuitry. So this was the objective of today's class. So in this we have studied how to merge two circuits of the transformer into a single circuit. And now there are two ways we can merge. Either we will merge secondary side into the primary side. So this is what we call as the equivalent circuit of transformer referred to primary, or we will merge the primary side to the secondary side, which is shown here in this slide. So this is what we call as approximate equivalent circuit of transformer referred to the secondary. Now, now why we have done this? Because this will make our calculation, make our analysis easy and convenient for the transformers. So this was all about today's class, and thank you so much.